Good morning, everybody. I'm happy to kickstart today's session on exploring spherical agglomeration with mechanistic understanding, where I'll be presenting some of our work on analysis of an immersion-driven mechanism. So for the outline for today's presentation, I'll be covering four main areas. I'll start off with giving a bit of context and a bit of background in terms of our work in spherical agglomeration and some of the hub activities. I'll then focus on some of the key rate expressions that we're using in order to build a mechanistic model from ground up, and how we then apply that to some of our predictive capabilities, such as a population bounce model to predict product attributes. And then finally, a few results to just wrap up on the analysis of the process model and its capabilities. So in terms of background, spherical agglomeration, it's an increasingly applied technique for pharmaceuticals. It's been used primarily as a particle size enlargement technique, which uses an immiscible bridging liquid. And it has a wide variety of applications, including pharmaceuticals and other high-value products as well. One of the key benefits and drivers for applying it is that it can be applied to problematic and difficult to process shapes or particles. So, for example, if you see here, you have needle-like crystals. And by using the immiscible bridging liquid, we can form these really nice, dense and enlarged spherical agglomerates, which inevitably will make downstream processing easier as well. And within the hub program, within phase one, there have been many examples and many proof of concept demonstrations, really showing on how this technique can be applied as a process-intensified unit operation and how it can be integrated as well. And one of these has been the hub lovastatin microfracture, which has been previously shown. Within our work in Sheffield, one of the key areas that we've been focusing is the mechanistic understanding, because there's still a great need and a strong need for fundamental understanding, particularly around the particle-liquid and particle-particle interactions. And this is still becoming really important because if you think about it, this technique is still within its infancy stage of research and development. So when we talk about mechanistic understanding, one of the things we want to understand is what are the key mechanisms and key rate processes involved. Because if we can understand these key rate processes, we can then start building our models, which will provide a foundation to control and predict agglomerate attributes. And of the work that's been done today in some of the known literature, there are two mechanistic pathways that are often quoted and can occur during the formation of agglomerates. So for the first mechanism, we have the immersion mechanism. Well, I should probably say before then that these mechanisms are essentially controlled through the relative size ratio between your bridging liquid droplets that you add your immiscible binder liquid to the suspension of primary crystals. Okay, so in the case when we have a smaller bridging liquid droplet size compared to your crystals, a distribution mechanism takes place where we have the coating of crystals around the droplets. On the other hand, the immersion mechanism, if you have a larger bridging liquid droplet size being added to your suspension of crystals, which are smaller in size, we see the immersion mechanism where this time we have the gradual encapsulation of crystals within the bridging liquid droplets, forming, again, these really nice, dense spherical agglomerates. In terms of preference, we tend to work with the immersion mechanism, which has been our focus for the past couple of years. But as you know, with many processes, you can have different end products. So similar to crystallization processes, depending on where you're operating, which regime. This was some work actually done by within the Cmac core project by Dr. Kate Pipp, where she showed different end products showing a mixture of primary particles and agglomerates, and also some strong agglomerates as well, and a paste-like material. So you can see that where we ideally want to be is within forming these strong agglomerates, which will enable and enhance downstream processing. Okay, so one of the tools that we can use for our predictive and modeling strategies has been the population balance. This has already been applied quite extensively now to crystallization, and I know there were some examples shown yesterday. But essentially, we can apply this tool to any particulate process involving the transformation from a liquid to a solid or from a solid to solid. And we can do this by defining our control volume. In this case, we can also refer to it as our particle generator. And by specifying your inlet size distributions and your key rate processes. So, for example, in our process, we've identified the mechanisms that we want to model, which are the nucleation, the consolidation and growth of these agglomerate nuclei, and then the subsequent coalescence growth of these agglomerates as well. And we can do this through providing key rate expressions, for instance, for the growth term, which accounts for the layering mechanism, which essentially is a differential growth term, and also the birth and death processes, which account for the sudden appearance and death of particles as well. So just spending the next couple of slides on these rate expressions. For the nucleation, the agglomerate nucleation aspect, we assume that it occurs upon the addition of the bridge and liquid droplets when they're added to the suspension of crystals. And so we can account this within our birth term, which involves the number density and the volumetric flow rate of your droplets being added to the suspension. One of the key assumptions here is that once we form these agglomerate nuclei, we also assume that they have an average liquid volume fraction of 1, which means we're saying it has the same droplet size and the same volume as our bridge and liquid droplet. That's important because then it allows us to distinguish between the kinetics of wetting of crystals by the bridge and liquid droplets and their subsequent growth by layering. So in terms of how do they actually consolidate and grow by layering, again, we describe it through a differential term, growth term, where in this case we have two regimes that can occur. So for the immersion rate limited regime, depending on, so I'm not showing here, but there's a dimensionless number that was developed, which in the case where we have an agglomeration number greater than 1, we have an immersion regime, which is limited by the immersion of crystals from the surface of the droplets into the droplets itself. Whereas the collision rate regime, this is now limited by the subsequent arrival of crystals to the surfaces of the bridge and liquid droplets. So we can describe these mechanisms, but a key thing to note here is that they both have this constant liquid, this constant packing of crystals on the surfaces and this subsequent suction and immersion of crystals within the droplets. And just to show the differences in how do these two different regimes operate and grow, the main thing I wanted to highlight here was for the collision rate regime, it's a very fast process compared to the immersion rate. So in this case, you can see that the agglomerate nuclear size increases quite rapidly compared to the immersion regime. And we track this both for the collision, for continuous and batch processes as well. Okay, so now just coming on to further growth of agglomerates via bicoalescence, and how do we actually go about modeling when particles come into contact with one another. Again, within our population balance model, we would need to describe both for the birth of these agglomerates and also the subsequent death of these agglomerates. So if you think about it in terms of a binary coalescence process. But the main thing from here is that within both our coalescence terms is that we have our birth and death terms, we have the coalescence kernel. And within the coalescence kernel, we define it based upon the meeting probability of the agglomerates and their efficiency, their coalescence efficiency. So how does this work? Well, the meeting probability is essentially the function of the target efficiency, the characteristic sizes of these agglomerates, and their collision velocity as well. For the subsequent efficiency, and if we solely relied on the meeting probability mechanisms, we'd probably see an endless process to the formation of agglomerates. So we need to essentially correct for the meeting probability by including a sticking force. And what this denotes is that if the adhesive force is greater than our separation force, we see this gradual coalescence of agglomerates forming these really larger agglomerates over time. If the shear-induced separation forces being acted upon the formation of agglomerates, or when they come into contact, is greater than the adhesion force, then we'll see the subsequent separation of these agglomerates. And in that case, we probably wouldn't be having any coalescence of your agglomerates. So just in summary of how these mechanisms were then incorporated, we then customized our kernels and included it within the population balance model, which is available in GPROMs and it's subsequently solved in GPROMs. And this allows us to predict several properties and attributes, such as the size and size distribution and the average agglomerate liquid volume fraction as well. I'm not going into the material properties and process parameters. You can find me in my poster, so I'm happy to talk more into that. But just wanted to focus mainly on how we're including these models within the rate parameters. And once we developed the model, we wanted to understand how it was behaving, particularly on the bulk formation of agglomerates. So we ran some sensitivity analysis checks. But you can see from graphs A and B is that within the plot A is that we have a gradual addition of a bridging liquid. After addition, you see that the mechanisms almost come to a halt or a steady, almost a final equilibrium state after when your bridging liquid is finished as well. You can see still formation of agglomerates after that phase, but a lot of the mechanisms will be happening during your formation of your bridging liquid. So this is quite powerful because here we can start to decouple when and which type of mechanisms are occurring in our model. And also within the model, we were able to track different populations, so the population of agglomerated particles and the population of unagglomerated particles as well. I'm not going to go through every single graph, but here I just wanted to highlight that we did a thorough sensitivity check as well, looking at which formulation and which process parameters had the most profound effect on our agglomerate attributes, and we found that the droplet size of the droplets adding to the reactor and the bridging liquid to solids ratio had quite substantial effect, not only in terms of the kinetics, in terms of the agglomerate formation, but also of your final product attributes as well, such as the final size that was generated. But you can see the droplet size, through increasing the different size values, we saw quite a substantial increase in the final agglomerate size. And within the BSR, as is quoted in the literature, we found this optimal range that often exists where agglomerates would form. But if you increase more bridging liquid afterwards, you'll probably enter this into a paste regime. So we ran these and it was quite interesting. And I just wanted to highlight here that the model is also capable of tracking both your two modes, so your primary particle size mode and also your agglomerate size modes as well. We also looked at the performance of the model. So we tested these for this for a lovastatin agglomeration system, which consisted of MIBK, of bridging liquid, and water. So this was taken from data from Francesca, previously from her PhD in Strathclyde. We did some checks as well within Sheffield, but we found generally good agreement of the model with the experimental results. There was some slight discrepancies which could be due to other mechanisms that were yet to develop and include, such as breakage and attrition. But overall, we saw pretty good agreement with the material system of study that we investigated. And as was stated yesterday, when developing these models, it's always important to run a wider sensitivity check to see the feasibility and the performance across different ranges and very wide ranges as well. So we've been doing some tests as well, looking at different droplet sizes, different primary particle sizes, and also the effect of the individual model parameters and which model parameters are important for the overall process model. And we can do this quite comfortably in GPROMs using several global analysis tools, such as the Sobel indices, but also uncertainty analysis as well. Okay. So just to wrap up the presentation, so probably just a few key points from the presentation is that a predictive population balance model has been developed, and we can start using it for spherical agglomeration process design. Of the study that we conducted was that bridging liquid droplet size and BSR were found to have the most influential parameters on both on the kinetics but also on the attributes. The mechanistic model that was developed incorporates some of the key rate phenomena and can be used to predict several attributes, such as a primary particle size, because often within an agglomeration process, you have two modes within your final distribution, but not always as well. However, going forward, there is still some further development and introduction of new mechanistic kernels for spherical agglomeration, which I think can be really developed and learned from the already established wet granulation literature that's been out there as well. So I'd just like to thank all the collaborators, particularly the team at Sheffield and also the Cmac Hub team as well. And if you want to find out any more information on modeling spherical agglomeration, please feel free to visit me. Location, conference room 405. So thank you very much.
So that's the top round introduced there. Talking around hybrid modelling, what it is and some of the applications we've used in it. Again, Alistair touched on some of this. I'm not going to go into this detail, but you'll see more of this throughout the day and through talks and posters. And this is the Cmac workflow called Quality by Digital Design. But at its core, what we have is essentially a digital twin and our data microfactories. And when these, our digital twin encompasses all our models. So it covers anything we're using to model a process that feeds into our microfactories. As we touched on before, and is increasingly what we're doing now is actually using our models first to drive our data microfactories and design our processes. But we know our models aren't perfect, so we also have this feedback loop in terms of improving our models, where our experiments improve our models. One of the things we've not really touched on, and actually Tony was starting to touch on this yesterday, was what are these models? And so there's a range of different approaches for this. So I don't want to copy Tony's slide, but it's essentially the same thing as he showed yesterday. You can think of this as two different camps. We have first principle, mechanistic, physics-based models, or white box models, depending on your background. And in these models, we know the process mechanisms, we apply the laws of physics, but generally we have to have some idealization and some assumptions made to make these models work. On the other end of the spectrum, we have data-driven, machine learning, black box models, whatever you want to call them again, depending on where you come from. And these just infer an input or output-input relationship. We don't really need to know the process, we just need a whole bunch of data. But the limitations of this is that obviously it's only really valid within the data set that we train these models. However, we shouldn't really think of these as sort of distinct conflicting approaches. And this is where the idea of kind of hybrid modeling comes into approach. So what we can do is actually think of these more as a spectrum, where we can couple these models together. So on the far left is our first principle models, where it's purely mechanistic models, and on the far right is our machine learning models or data-driven models, where it is those data collection to develop the models. But there are a number of different ways in between these two that we can couple models together. So for example, the first one to the left, this one here, this example that Tony gave yesterday, which was fantastic, I think, we've got a first principle model for solubility prediction. It's not perfect, we know there's errors, so therefore we apply a machine learning model to correct for this. On the other end of the spectrum, we might have a machine learning model for a process, but we can't collect the inputs for that model directly. Therefore, we could use a first principle model as like a soft sensor or model-based sensor to feed into that machine learning model. So this is just a sample of what's shown here. There's a range of different ways we can couple these together, but no matter what way we do it, we can rank them on this sort of scale of availability of first principle models. So with a couple of examples I'm going to talk around today are where we're applying these approaches. So in the first common approaches you'll find with these is the idea of surrogate models. So this is the idea of I've got a first principle model, but for some reason I don't want to use it and I need to replace it with, for example, a machine learning model. So, but why would we might want to do this, okay? So this example, you'll find posters from Alex and Cecilia out on the level 3 in this one. So why would we want to have a surrogate model? So if we think in the process environment, if we're looking to develop a process, we're really limited by the equipment that we've got. Okay, so if you do a crystallization in a stir tank, yes, I can change the stirrer, yes, I can change the RPM, I can get different shear rates, I can get different heat transfer, mass transfer, but it's really a limited range. In the idea of a generative or an adaptive design approach, the reactor design becomes another variable. So the reactor itself becomes something like temperature or pressure or flow that we can optimize. And to achieve this, we have a workflow where initially we have to define our design space. We have an objective, we know what variables we can adjust and what our constraints are. We use this design space to generate a whole bunch of designs. There's a range of different approaches we can do with this. We take our designs, we analyze them, we look at performance metrics, how did each design compare. We can rank our designs, we can choose the best performing designs and loop around this. And that might seem like a traditional equipment design approach, but what's different about this is we do this all in silico. So this is all using models, and as it's all coupled together, we can go around this loop in an incredibly fast space and generate thousands of designs. And this is an approach that's it comes from product design. You see it quite a lot in lightweighting, so brackets and things like that, reducing weight but maintaining structural integrity. But here we're looking to apply it to process design and equipment design. So what might this look like in our case? So we've got up here a design. So this is a coil flow reactor. So essentially it's a bit of coil pipe that spins round on itself. And that is characterized relatively straightforward for a number of geometric parameters. So the diameter of the pipe, diameter of the coils, number of turns, layers, etc. So we can design these, and we can do these in CAD. There's a number of parametric approaches of designing these models. We then need to analyze this design. So what is the output for this? In this case, we're interested in things like resonance time distribution, pressure drop, shear rate. If we include chemistry, we look at kinetics, yields, conversions, things like that. And then we can obviously have all these performance metrics, and we can rank our designs and choose which model we want to look at. The problem with this is we need to do some CFD here. In the lightweighting sector, you can create a gradient essentially between your surface and your structure and your stresses and strains in the bracket, which makes it quite an easy optimization problem. Whereas here, we can't do that. We're not relating the surface to stresses and strains. The surface defines the volume and the flow defines our CFD, which gives our resonance time. So there's a few more steps we need to do this. We need to do some CFD models. Anyone that knows CFD tells you it can take time. So for a simple coil like that, where it's only maybe 4 loops, it can be fairly straightforward. But as these coils and designs get more and more complicated, we add more layers, the problem gets more exponentially more difficult and takes much longer to solve. So how can we speed up the CFD simulation? Now, this isn't the way of doing it. There are multiple ways of doing it. I'm going to show 2 examples here. Obvious one would be brute force it. We talked about it yesterday about compute power. Throw lots of high-performance CPUs at it. There's even companies like M-Star you'll see in the exhibitors, where we're using GPU-accelerated approaches for CFD. Essentially brute force it. Yeah, lots of compute, lots of solve it. But again, the problem still becomes, as complexity, you do hit that bottleneck again in terms of the time to run these models. So this is where we can come in with the surrogate model. So what we can do is we have a design space here. We map out roughly where the extremes of our process. We have CFDs for the extremes of the design space. We also have ideal models. And also, crucially, we have experimental data. So it's not just a surrogate model that replaces our CFD model. It pulls in from other different models and other different characterizations of these designs as well. So actually, within this, we include experimental variance. So how good is my probe performing? What is the limit of detection of my probe? So for all these designs, we determine performance metrics. Again, that's a resonance time distribution, etc. And we can train then our machine learning model to correlate our geometry parameters of our design to our outputs, be it whatever performance metrics we look at. And performance varies. So you can see on the right-hand side here, these are some examples of just actual versus predicted of the range of the meta models or surrogate models that we've developed here. So that's one approach. One of the limitations of that, though, is that if we want to add more performance metrics, or if we want to expand the design space, we need to go back, retrain a new machine learning model, or we need to do more CFD models to give us a bit of design space. But what if we can do the CFD much quicker as well? So Jonathan, I think, touched on this yesterday, the idea of convolutional neural networks. And what we can do is we can couple these with ideas of what's called Lstm, so long short-term memory models, that help us predict sequences. So we've taken our coil there, we've essentially sliced it up into little segments, and now you can see the flow pattern. It comes down here and it goes around here. So you can see the flow pattern develops with that. And what we can do is we can use these convolutional neural networks and our short-term memory models to predict the sequences. So for example, if we give the model, here's our first 3 points, what's the CFD prediction, so what's the CFD ground truth, and what's our model prediction. And you can see here for a range of different sequences, we actually get pretty good performance out the box. So our CFD ground truth here, you can see these are Dean's vortices forming on the edges here, which our model also suggests. Again, in the second sequence here, we get the left and left, and then right and right. So the model, our neural network model, has actually been pretty good here in terms of learning the performance of this. So this helps us maintain the fidelity of the CFD model, but does reduce the computational load, because we don't need to simulate the whole coil. We can just simulate part of it and then extrapolate what the rest of that would be. As I said, there's a range of different ways we can do this. Regardless of how we do it, the output is what we can do is we can solve this design loop much, much faster than we could before. So instead of taking weeks and days to solve this loop, we can actually go through, again, thousands of designs within hours and evaluate all these designs. So some of the animations you're seeing there is basically an optimizer working through a design space and generating all these coils, analyzing the performance, and outputting the metrics. So that's one example. The second one I'm going to talk around is how we couple first principle models and machine learning models, not only to make predictions, as they usually do, but also understand what process parameters are critical. So I won't go into the details, but most people will know primary nucleation is very stochastic. It's determined by a number of different hydrodynamic conditions, different impellers, stir speeds, modes of mixing, etc. So if we want to do scale up between different vessels or different geometries and do tech transfer, we need to know what we're going to scale up on. And look in textbooks, there's things like Reynolds number, tip speed, power density that we can use to do this approach. But sometimes these aren't sufficient. So what can we do here? So first of all, what we did was we collected a range of induction times across a range of scales, so from 100 mil up to 10 litres. All we varied was the stirrer speed, the stirrer type, and as I said, the volume. Compound, solubility, supersaturation were all kept constant. So we did this across a range of different scales, collecting induction times. From this, we can apply classical nucleation theory and determine a number of parameters. So we've got J, our primary nucleation rate, and TG, which is a growth term, which is a really coupling of secondary nucleation and growth rate. And parallel to this, we can characterize all our designs. So here we generate something like 30 different descriptors of our CFD, of the hydrodynamics in the different vessels. We know the vessels aren't homogeneous, so we've looked at distributions. So not just the mean of each feature, but also things like the quantiles at 10, 20, 50%, things like this. With these two, our features and our targets being our J and TG, and our features being our hydrodynamic characteristics, we can train a whole bunch of machine learning models. There was something like 30 different models trained here, covering a range of different algorithms, a range of different feature sets. I'm not going to go into detail of all of them, but essentially the univariate models, where we try to correlate nucleation with, say, tip speed or Reynolds number, were pretty rubbish. So what we ended up using was really nonlinear models that coupled multiple parameters together. And actually, we got pretty good at the end in terms of the training set and the performance of those. Now that we've got a model trained, what we can do is actually try to interpret that model and understand what it's doing. And Jonathan, I think, again, touched on this yesterday from the chemistry space. Does our model learn some chemistry, and what can we learn from that chemistry? In the interest of time, I'm going to kind of skip over the top one, but the lower one here, essentially, what we're doing, we're applying some out-of-the-box tools called SHAP and LIME, which allow us to determine some of the explainability of the model. So what you see here are some of the performance, some of the features of the hydrodynamics that the model thinks is important for our process for looking at nucleation kinetics. And although these two models on the left and right here have similar performance in terms of predicting nucleation kinetics, they consider things differently. The left-hand one really looks at kinetic energies, and the right-hand one looks at velocities. So the question then becomes which one is correct. These are different terms. But what we can do is we can use the model to design experiments to help us determine these different, which model is the correct one, using a model discrimination approach. Regardless of what we do, we always need to validate a model. So here we can see once we've been through all this, we can actually predict external sets. So here we have samples of different scales, and we're predicting the induction time distribution here purely from the hydrodynamic conditions. And as you can see, if we look, for example, across the 50th percentile here, we're actually pretty good in terms of the order of magnitude and the values there on the induction time. We do see a bit of deviation at the tails here, but in terms of, again, that order of magnitude, these are pretty good models that we've got here. So what have we done here? So we've applied two different first principle models. We've got classical nucleation theory, we've got CFD for fluid dynamics. We've then looked at machine learning and applied this as a tool to look at correlations and causations between these modules. And then we've applied first principle models to do predictions at the end. So we're not only using machine learning models here as a predictive tool, we're using it as an analysis tool to understand the features of our models and our first principle models and see what is important when we're doing scale up or tech transfer, for example. So just some points to take away, to reiterate. As you'll see more and more across the day, experiments are always going to inform models. Models aren't perfect out of the box, but more and more we're using models to inform our experimental plans. First principle machine learning models shouldn't really be thought of as distinct, separate approaches. Think of them as a continuum. You can integrate them, they can talk to each other, and you actually get more benefit from these. Again, I could have ended this talk with pointing to Tony's talk yesterday. I think that's a fantastic example of where the performance comes to these approaches. And then last point, it's just another tool to gain insight in terms of process modeling. These aren't designed to replace any other model tools. They are just another tool to help you understand your processes. And then just to wrap up as well, thanks to all the collaborators within this and funders who've contributed some of the material for this talk. And thanks for your time, and happy to take questions.
So we've Alistair briefly mentioned earlier today that we're moving towards this lab of the future, and you've heard about different components of this lab. For instance, the augmented and virtual reality we talked about yesterday. Cameron briefly mentioned the quality by digital design workflows, which are leading this, as did Blair, and Murray in the next presentation will go into this in a lot more detail. And then we've also got some robots here. So that's what my talk is about today. How do we bring mobile robotics into this lab of the future, and what's involved in incorporating these and getting them to work with the instrumentation that we already have. So I mentioned the quality by digital design workflows, and as Blair said, it's important to recognize that this work is not done in isolation. There's the arrows that come in and out of it. So, but where we sit here, so we're thinking about how an API goes through Cmac and its journey along the way, and it encounters the digital twin, the data factory, and the microfactories. And we're looking at the data factories here, specifically a small-scale cooling crystallization data factory. And for more on this, please come to poster 64 for the details. So, but why do we want to bring mobile robotics into the lab? There's some excellent robotic platforms where everything is contained within a single robot. But the reason why we want something to walk around, a cobot that mimics what we do, is that this allows us significantly more flexibility to both incorporate the robot with existing instruments that don't have such capabilities, but also as we move towards the future, we can adapt grippers or introduce new grippers and bring on more and more instrumentations as we want to expand the capabilities of an automated data factory. The advantages of having a robot in the lab is that it works 24 hours a day, 7 days a week, once we get it up and running full time, and this will allow us to immediately quadruple our output of experiment collection as we're looking at solubility, different kinetics for these crystallization experiments. So that suddenly we're not running our crystallines 8 hours a day, but 24 hours a day, and on the weekends as well. It also means that because of how we're collecting data on the experiments in real time, and we're doing analysis in real time as well, we can adjust experiments in real time and say, oh, after 4 hours, I'm going to shut this down because I'm not getting any more usable data, and I'm not going to waste that 4 hours of experiment time. So additional optimization and improved output. So as we're gaining all this data, we can also move towards not just automating it, but making an autonomous platform that makes decisions for itself. So why autonomous? And that brings me a little bit back to the workflows. We can use these workflows to guide our way through this pathway. And as we're collecting many different types of data, we can feed this data back in to make decisions about what experiments we want to run next. And not only explore the data, the space, but we can explore optimally. So we're collecting enough different types of information to make it useful for machine learning, but also doing this in an optimized manner so that we're not wasting our time on experiments that we don't need to run. Where I won't get too much into the models, but as Cameron was talking about the design space and how these optimizers can work. But once we start collating all of this information about how APIs in many 30+ solvents crystallize, we can start predicting how APIs we haven't looked at will crystallize in solvents that haven't been used for that API, and start saying, oh, maybe someone gives us an API, we can recommend a system via very few experiments, and that will work for industrial scale crystallization. So that is our eventual goal, moving towards a crystallization classification system. But now we've looked at what our motivations, let's look at how we make this happen. So we start off, we've got some information coming in from the QED workflow. So you heard Tony's talk yesterday, so we're looking at solubility predictions, and then as we take experiments, as you saw from his one experiment, can significantly improve those predictions, and we're easily going to do 5 experiments to make it better and better. We're also bringing information in such chemical information via molecular descriptors, among other things. So in the center here, we've got our puppeteer master, or conductor as it were, a control PC that's running LabVIEW that can call out to all these different instruments that are involved. So this is what we're currently bringing online. So there's one manual step. We do actually need to bring the APIs and the solvents to the robotic dosing platform and put those in. And then we feed this data into the control PCs to ask it to plan the next experiment. Once we've got, let's go back. Once we've got that, the experiment planned, we reach out to the mobile robot, say, please close the door and make sure the Zinsser dosing platform is all up and ready to go. The Zinsser will then dispense the APIs and solvents that you've loaded into it. It then reaches back to the control PC, says, I'm done. Now direct the KUKA robot here to transfer vials from here all the way to our crystalline platforms on the other side of the lab and load them up. And once the KUKA is finished, it will then talk back to the control PC, tell it, I'm finished. Can you ask those experiments to run now? And once these experiments have finished running, this will then, again, talk back to the control PC, say, you can now tell the KUKA to analyze or dispose. Again, that's the opportunity for future experiments there. And then while this is all happening in the background in the control PC, we are creating this database for machine learning and also referring back to this database to say, oh, what's my next best experiment to run? So this is what the physical reality is starting to take shape in our lab looks like. And the data we're collecting, I won't go into too much detail on this, but please do visit Chris's and Thomas's posters, 22 and 66, as they both do a stellar job of talking about this. But we've got image analysis that's going on as we watch the crystallization happen in real time on the crystalline platforms. And we're picking out particles so we can track growth rate, size rate, just the particles that are in focus so that we know what size they are. And then we can pick out more particles to track the nucleation rate as well. As we go scan through the design space, we're collecting solubility curves for all these APIs across 30, not quite 30 here, but there will be solvents. And then there's some offline analysis that needs to be coupled to this to account for making sure that we're making the right polymorphic form as required by regulations. And right now we also have visual inspection for any agglomeration or fouling or phobic materials if an API really doesn't like being in a particular solvent. So this is the data that's feeding back into that machine learning database and allowing us to make these autonomous decisions in the future. So now let's look at bringing the robot into the lab. So day one of getting the robot up and connected to the computer, the first thing you do is you get your robot to wander around the lab with its laser scanners and map out what it can walk into as it goes through. So in gray, we see this is like the no-go bounds, and this up here corresponds to the Zinsser platform. We've got its charger down here, the control PC, the crystalline, and the sink. And here you can see it's a sped-up movie of the robot moving back and forth on its merry way in between the two instruments. So you can see we've got a turn in the middle there, and that's because the mobile arm is on one corner of the robot. So to fully take advantage of the robot's reach, it does a little spin in the middle. So we've got the base up and running, and then once it gets to either side of the lab, it needs to do more. It needs to reach out, pick things up, and grip. So this is a simplified robotic behavior tree, and we've got about 50% of these behaviors programmed into our robot right now, whether it's the base moving back and forth between the instruments, the arm reaching into the different instruments, or the gripper picking up vials, vial trays, vial tools, or the vials themselves. So I'll give a video of the robot in just a second, but let me first talk about where we're going next and what we're already doing. So there's that automation, making it automated and integrating all those bits and pieces. So we're working on the connections in between the Zinsser and the control PC and the crystalline and the control PC. And the KUKA also, of course, in the control PC. So we can automatically sweep this design space and start collecting those high-throughput experiments data. Then as I mentioned, alluded to earlier in my talk, that we can expand these future capabilities of this robot. And because if you want to crystallize an API, you don't just care about how fast it's going. I mentioned we have to do all these offline experiments for physical form or visual inspection, but we can start bringing these in by maybe adding an offline, a Raman probe that was offline, but maybe the robot now reaches into a black box and puts the vial in and says, all right, now collect me a Raman spectra, or collect me an XRPD pattern, or look at this camera. Does this camera use some image analysis to look for agglomeration and fouling? So again, we're going to keep expanding this. We've identified a very quick way of bringing another crystalline platform. We'll immediately double our output of these experiments. And again, all working towards this crystallization parameter database where we're feeding information back into the digital twin models, both experimental conditions, but also kinetics and parameters with associated uncertainties. So as we're going through more and more APIs, we're going to be interested in finding more and more APIs. So if you've got a big, say, a kilo of API sitting around, please come bring it to us so we can run it through our data factory and tell you what solvents it performs well in, plus much other data. So with that, I'm going to run a teaser of what's going to happen in the lab demos in case anyone's not attending. And if you are attending the lab tours, you'll get to see this in person as well. So there's some music with this video. Hopefully it's not too loud. So I just want to say thank you very much to my colleagues in the Search Lab for helping make that video happen for today's talk. A quick call out to some of the posters I mentioned. Please go see Thomas's poster for that solubility screening, kinetics, nucleation information, Chris's poster for and demo of that image analysis for looking for particles, Tony's poster and demo for the solubilities predictions, and then Faisal and Mohammed are also working on similar projects, Mohammed on decision making, Faisal on the robotic side of things, so check out their posters as well for a little bit more information. And with that, I just want to say thank you very much, and any questions?
So what I want to cover here is quite a lot of what I'm going to cover in the next 10 minutes is kind of been touched on yesterday and the previous talks today, but I'll just go into a bit more detail. So first of all, I think practically every presentation so far has mentioned the words digital twin. I will just quickly give the Cmac definition of a digital twin and basically put it out there as to our vision of that. Again, the previous two talks quickly talked about the quality by digital design workflow. I'll just go into that a bit more detail. And then following on from that, basically my role working towards digitizing this workflow and structuring all the data with it. And then finally, I'll introduce what I'm demoing outside in conference rooms 4 and 5 is the Cmac Digital Twin app, which is basically a mobile-based application for basically exploring the microfactory setup we have in the lab upstairs, basically so we can interact with the data and use it as a bit of an educational tool, but also a visualization tool for real-life problems that we have in the lab and how we want to visualize the data. Okay, so the Cmac Digital Twin, or the Cmac definition of the digital twin. It's not just a single flow sheet that defines our microfactory setup. Our vision of the digital twin, it encompasses everything. So all data, all models, and all knowledge around a process is what falls under the umbrella of the digital twin. This also covers materials used, products used, and processes. So it's the central location for all the information on how a process has been developed and designed. This is obviously built on a foundation of data, and more importantly, this is experimental and simulated data. And the pathway for gathering that experimental data and simulated data has been driven by the quality by digital design workflow, which I'll come to. And why bother? Ultimately, we want to design processes and control strategies for our microfactories and basically transfer that from a computer, from multiple models, and basically to transfer that to a right first time operation of a microfactory. Chantal and Cameron touched on this, and this appeared in several slides yesterday in different iterations. So this is our quality by digital design workflow. Please don't, the screen is quite big, you don't need to care, the detail doesn't matter here, the individual boxes. This is also work in progress, and as Chantal said, the poster outside, we are looking for feedback and things we have missed. We are aware this is still a growing monster. So take home from here is basically every box at this level is basically a workflow. So basically inside each one of these boxes is another slide as complex or even more complex than what's on the screen here. So it's there's a lot of moving parts from the beginning to the end, from the selecting the molecule to having a drug product at the end. But we can break this down, and as we've seen before this morning. So first of all, there's just the microfactory development workflow across the top. Sitting underneath that is a digital twin, and the digital twin controls everything else. So as you move along the microfactory workflow, you then speak with the digital twin, check what data is there, check what model's there, what model data and so forth. If experimental data is missing that would help validate a model or is required to continue a stage, that then gets triggered into the data factory. Now, the concept of the data factory, yes, it does encompass what Chantal's just talked about with the fully autonomous system, but the data factory is also, we don't have robots everywhere, so sometimes we have to resort to using humans to generate the data. So at the moment, the majority of the data factory work is triggered by actual human beings in the lab rather than robots. Robots are not going to take over anytime soon, hopefully, for some of our PhD students. And then this data is then collected, passed back to the digital twin, and then back up the stack. And then again, as you move along the workflow, you get towards the end, back down digital twin into the microfactory, and hopefully right first time we design a process, we go in, set up the process, and it runs as expected. So my job and what we're trying to do, because this is still very much the early days of basically digitizing this QBDD workflow and how we're going to do it. So in each one of those boxes, as I said, each workflow basically needs has a continuous loop until the decision criteria is met, and then it passes on to the next stage. So going around this loop, basically the master workflow calls out to the digital twin, looking for some supported intelligent decision to prompt the next experiment required. This then passes into the data factory or the microfactory in the later stages to trigger an experiment to be carried out either by the robots or by the guys up in the lab. Focusing more on the data generated in the lab by people, so as it's less structured. Chantal touched on the last question Chantal just had to deal with was the data structure and the metadata capture within the autonomous data factory is a lot easier to control, so it's easier to structure, and there's less issue there. In the lab, Tiff touched on it yesterday, all different types of file formats come out, some proprietary formats. We need to get the data out of those files. So we then go into extraction and transformation, what Tabson was speaking about yesterday. So we need to extract and transform this data to help harmonize the data as well. So harmonization, there's sometimes more way to generate the same data. Different instruments can basically end up in the same at the same destination. So we need to harmonize that because measurements, how data is described, essentially the metadata is different on different instruments. So that needs to come together. And then finally, it then gets loaded into our structured databases where it can be queried and visualized and whatever. And then the bottom section here, this ties in nicely with Tony's talk, a really nice example yesterday. New data can then be used to validate and improve the models. So we're currently working, myself and Tony, so his models work off live data sets. So basically whenever new data is available, and he's working off the most up-to-date, he has the most up-to-date model, and things are continually improving. And we have other examples of that kind of in the pipeline in the labs just now as well. And then finally, this kind of completes the loop, and the loop basically continues until a decision point is met, and the QBD workflow continues into the next stage, and then so on and so forth along the top line of the QBD workflow. So moving on, and just quickly cover what I'm demoing outside. So in collaboration with Victor from the Glasgow School of Art, collaboration with the Glasgow School of Art with the help of Victor, we have taken on developing this concept of the digital twin app. So what we intend to do, or what our vision of the app is, it's it's meant to be a user-friendly interface to basically explore microfactory data. Longer term, we intend this to be a modeled data and process data. So visualizing data from the lab is, at the moment, it's quite a struggle. The microfactory is quite a complex setup. There's lots of data sources, and basically pulling all that data together and how to visualize it has been a bit of a challenge. So we thought about, well, let's put this into an app, make it as interactive as possible, and see how that goes. What we're demoing outside and what we've done to date is basically built a prototype of this, basically based on modeled data. Basically, so it was a more complete, a larger data set to work with. And then what we can do here is basically 4 stages. There's 4 stages of the microfactory we've been concerned with. So the wet mill for seed generation, the MSMPR crystallizer, filter wash dry rig, and then DISO testing. So the theory in the app is you can go to each unit operation, you can change several parameters, change the settings, and then basically view the output. And as you change outputs, you should be able to, in real time, see the changes in the outputs. So it's been built on the Unity platform that Victor was talking about yesterday. So we have really nice high definition 3D rendered molecules of equipment that is in the lab. So straight away, there's for the users, there's a familiarity with the equipment. They're not having to interact with something they're unaware of. We're also trying our best to basically make the interaction with the equipment as similar to as is in the lab. So, for example, in the wet mill, to go to the wet mill to change the rotor speed within the mill, you interact in the app the exact same way as you do in the lab. So far what we've done, we've just dealt with model data, and this ties in with what Cameron was saying earlier. It's a really nice, probably a nice example to adopt hybrid modeling. So to date, we've just done a very large GSA analysis within the unit ops, and it's still quite a conservative sweep of parameters, because we have just minimized it to 4 parameters. So mill speed, we have 5 settings, so we can put 5 different seed sizes through the crystallizer. The feed solution, we have 3 different flow rates. Agitation, there are 5 stages in MSMPR, and we've limited that to 3 different stir speeds, which is actually 243 combinations. And then temperature across the middle 3 vessels in the MSMPR, we've locked the first and the last one just to keep the numbers down a bit, was 35 combinations. So that already is a very conservative set of parameters that we're looking at, but is nearly 130,000 calculations. And for ease and simplicity, we decided just to let the GPROMs do that. It's probably not the most efficient use of computational time, and as Cameron touched on before, we can probably adopt some form of hybrid calculation to actually get more parameters for less computation time, which is something we've just not had time to look at yet, but we'll definitely be looking at the future. And yeah, as I said, future models, there will be a lot more parameters, so there's a lot more freedom within the model to explore. Future plans, yes, in the first stage, as I mentioned, let's reduce CPU time. Actually, sorry, and the final, just a point to make there. The 130,000 calculations, with the calculation of the crystallizer taking about 5 minutes of calculation, is 442 days on a single CPU. Now, obviously, we don't use a single CPU, so please do not think that a computer was churning away for 442 days to generate those numbers. We can spread out over multiple cores and reduce that down to, it was less than a couple of weeks to generate the numbers. Finally, future plans for the digital twin app. yeah, just as I was saying, more parameters, higher fidelity in the parameters, so you can be more precise in where we're exploring. We'd love to be able to incorporate lab data, so be able just to flick a switch and then view real data in the lab just to get an idea of how our processes have behaved, and can we overlay that with the modelled data, again, so we have an idea of model performance versus what's happening in the lab. And Victor touched on this yesterday as he was summing up his presentation. Where this leads to next is basically the integrating the data into the models was the hardest thing, and that's been the hardest thing to do so far. But now we've got over that stage. The next thing, and what we're really looking forward to doing, is augmented reality. So can we have Lab of the Future, put on your augmented headset and get look at a process and get live data from it, or can you use the augmented reality to design your process as you're looking at the system? So lots of exciting things ahead in the AR space, which is somewhere we're just going into this year. Finally, I didn't put in an acknowledgement slide because I had the fear of missing people off the acknowledgement slide. So instead of having a massive list of names, I would just like to thank everyone within Cmac. I have interacted with everyone. I have had feedback from as good as everyone, and I totally appreciate everyone's effort to buy into the cultural change, which has been quite a journey so far to move to the Lab of the Future, change attitudes to how data is collected, how we handle data, and data awareness in the lab. Also to the multiple collaborators I've had over the different projects I've been involved in over the years. It's all greatly appreciated. And finally, thank you for your attention.